Okay, now we're going to start our discussion of carbon nucleophiles. We're going to talk about Grignard reagents, and this is just a review of reactions that we learned back in the alcohol chapter, and then a new reaction that we'll learn is cyanohydrin formation. So again, back in the alcohol chapter, we learned that reacting an aldehyde or a ketone with a Grignard reagent will give us an alcohol. And we were particularly interested in this reaction because it also allowed us to change the carbon skeleton, add a new carbon-carbon bond. And because we're going from an sp2 hybridized carbon to an sp3 hybridized carbon, if we have a new chiral center, we'll get a racemic mixture, or we'll get both stereoisomers, because the Grignard reagent can attack from either side of the carbonyl compound. Now, the mechanism follows the same basic mechanism that we learned for nucleophilic attack in basic conditions, because Grignard reagents are strong bases, and actually they're destroyed by acidic conditions. So we have to do the Grignard reagent under basic conditions, but it's followed by just a very basic nucleophilic attack, proton transfer, just like we saw for the hydrides in the last video. Okay, a new reaction is the formation of cyanohydrins. A cyanohydrin is where we have an alcohol and a cyanide group on the same carbon. And so in these reactions, a cyanide ion is used as our nucleophile. And this reaction is reversible like a lot of the other reactions that we've seen. It's been found that this reaction works best under basic conditions. The mechanism for the cyanohydrin formation is the same basic mechanism for nucleophilic attack under basic conditions that we've seen before. We start with the nucleophilic attack and then followed up with a proton transfer. I don't need to add another proton source because the HCN is a sufficiently strong acid to protonate this intermediate. Now, we said when we first started talking about this cyanohydrin formation that we needed basic conditions, and HCN is a weak acid. So the way we create the basic conditions is to essentially make a buffer. If we add KCN, which is the conjugate base of HCN, we'll form a buffer. And if you remember from Chem 1212, when we have equal amounts of a weak acid and its conjugate base, the pH of that buffer system will be the pKa of the acid. And so because HCN is a relatively weak acid, its pKa is 9.3. So if I have equal amounts of KCN and HCN, I would have a basic solution. So by using both KCN and HCN as reagents, I have the source of cyanide ions, and I have the basic conditions that I would like. And just like a lot of these other reactions that we've recently studied, using hydride as a nucleophile, or in the Grignard reagents, when we're going from an sp2 hybridized carbon to the sp3 hybridized carbon, we'll get a racemic mixture if that ketone or aldehyde was not symmetric. Now, one issue with using HCN as a reagent is it's highly toxic. It's also extremely volatile, and that's a dangerous combination. So one way to avoid having to use HCN as a reagent, we can make the same buffer system by starting with KCN and then just adding a strong acid like HCl. Again, if you remember back from 1212, if I wanted to make a buffer, let's say I started with a solution with 1 mole of KCN. If I added half a mole of HCl, that would convert half of the CN minus into HCN, and I can achieve the buffer in the same way. So that's a way that we can get the same conditions without having to keep the toxic and volatile HCN around in the laboratory. So when I want to do this cyanohydrin formation, I like to use KCN and HCl as my reagents. So that's typically what you'll see me do. So one last note on these cyanohydrins is their synthetic utility. So it's relatively easy to convert this cyano group into other functional groups. For example, I can reduce it with lithium aluminum hydride to form an amine. I can also hydrolyze it with acid to form a carboxylic acid. So you don't need to worry about these mechanisms yet. We'll explore these more in the next chapter.